Hello, everyone, and welcome to my talk here at TARK 2021 about understanding transfinite elimination of non-best replies. This is going to touch on some pretty foundational concepts in epistemic game theory. Going to start right off with maybe the most basic idea in the field. Players should choose rationally, given their belief about opponent strategies. And players should believe that opponents believe that their opponents choose rationally given their beliefs. And players should believe that their opponents believe that their opponents believe that their opponents choose rationally given their beliefs, and so on and so forth. This is like a basic constraint. This is a set of basic constraints we can put on ideal rational strategic behavior in games. And we're going to call k layers of this reasoning plus rational choice, rationality, and up to k-fold belief in rationality. Now, what's called the fundamental theorem of epistemic game theory gives us a pretty intuitive implementation of that kind of reasoning. For any k, a strategy survives k plus one-fold elimination of non-best replies if and only if it is rational for a belief hierarchy that expresses up to k-fold belief in rationality. So far, so good. Now, in a lot of applications, we're naturally driven to games with infinite strategy sets. Think about quantity competition between two firms. They choose their production quantities. We don't really want to constrain ourselves to a certain quantity grid when analyzing that kind of situation. We don't want to assume they choose a milligram from a milligram grid or from a ton grid or from a pound grid. That shouldn't really influence their rational competitive behavior in that situation. So it's natural to let the firms choose from an interval of quantities. But as you might know from the standard Cournot competition, for example, then we also get those situations where we can keep on eliminating strategies infinitely many times. And we're going to have to ask ourselves, how does the fundamental theorem of epistemic game theory extend to these situations with potentially infinitely many eliminations, potentially infinitely many depths of reasoning. Now, something we know from a lot of nice applications and something we like is when things just extend pretty straightforwardly. Like in this picture here, we have the finite levels of elimination of non-best replies on the right side, finite levels of rationality, belief in rationality on the left side, and then all the way in the middle. On the one hand, we have elimination of non-best replies for all finite steps, elimination of non-best replies omega, and on the other hand, we have rationality and common belief in rationality. Now it turns out that this one-to-one situation only applies under certain assumptions about strategy sets and utilities, unfortunately. How it is in general was first studied in Lippmann's 1994 paper, and here's how it works. In a bunch of games, after we eliminated non-best replies for omega steps, we can just go on eliminating. We can eliminate for omega plus one steps, can eliminate for omega plus two steps, and it turns out we can construct examples where we can eliminate all the way up to the first uncountable ordinal omega 1. So then naturally the question is, what happens on the left side of the picture to the reasoning? What do all those transfinite elimination steps mean epistemically? Well, intuitively, we could think that the transfinite eliminations, how about they just work like finite ones? So for every step alpha, every transfinite step alpha, that comes with its own reasoning depth up to alpha-fold belief in rationality. Looks nice, nice extension of the fundamental theorem of epistemic game theory to the infinite world, but seems a little troubling if you think about it. Why? Well, now that would mean the reasoning in infinite games can be different and can be deeper than in finite games. So pretty radical difference between those two classes of games here, and a problem for how we use infinite games. Because, I mean, if you think back to the quantity competition example, why we really want to study the continuum of quantities there is because we don't want to commit to a large finite grid of quantities, but then that means we really let the infinite game stand in for the large finite game. Well, but then if the reasoning in the infinite game can be qualitatively different, how are we going to apply it to these real life situations? We can never be sure that what comes out of the predictions there is inherent to the real life situation and not just to those assumptions about infinite strategy sets. So that's a bit troubling about the intuitive interpretation. I'm going to propose a different interpretation in this paper that doesn't have that problem. Transfinite eliminations turn out to not correspond to depths of reasoning, different from the finite eliminations. And common belief in rationality actually is equivalent to up to omega fold or up to k-fold belief in rationality for all finite k in all games, finite or infinite. So what causes the transfinite eliminations? It's actually non-best replies, the tool that we normally use to determine the behavior consistent with common belief in rationality. That procedure loses information relative to the reasoning itself, and that's where the transfinite eliminations come from. Now, to illustrate this, I'm going to start you off with a little example. Here, Cournot game, standard Cournot game between players 1 and 2, indeed. They choose their quantities, like I illustrated before already, from an interval, 0-1 interval. They maximize this profit function here, increasing in the own quantity. Then it also increases in the market price, but the market price then decreases in the quantity I choose and the quantity I expect my opponent to choose. That's that integral at the end of the expression. So far, so standard. Now the twist is we have a third player, and that player, as it were, bets on whether the other two guys are going to settle on the equilibrium quantities or not. So he has a strategy equilibrium that's going to be optimal to the degree he was going to want to choose that, to the degree that he thinks they're going to choose the 1/3 Cournot equilibrium quantities, and his strategy non-equilibrium is going to be optimal to the degree that he thinks they're going to choose other quantities. Now, let's apply elimination of non-best replies to that game. As you all know, we're going to need countably many steps to of non-best reply elimination to select the 1/3 quantities between players 1 and 2. Now, given player 3's utilities, once it's clear that the other two guys are going to choose the equilibrium quantities, he's going to strictly prefer A to N, E to N. So after omega plus 1 steps of elimination of non-best replies, another choice drops out, choice N for player 3, and we end with a unique choice E for player 3. So what about this choice N now? Survives omega steps of elimination of non-best replies. So we can ask ourselves, can we then also rationalize N under up to k-fold belief in rationality for all finite k? It turns out the answer is no. Why is that true? To understand that, we have to look at not only the strategies that survive for player 3 at different levels, we also got to look at the first order beliefs for player 3 that are still consistent with different reasoning depths. This looks all a little complicated. The idea is pretty easy though. As we go through those layers of rationality, we already see from elimination of non-best replies that the set of quantities that the other two players can choose shrinks further and further. And for player 3, that means at up to k-fold belief in rationality, he has to believe that the other two players are going to choose the quantities consistent with up to k-1-fold belief in rationality. So we get this law of motion that I wrote down here. And if we let the k go all the way to infinity, both of these intervals that we see are going to shrink to the 1/3 quantity vector. Hence, after going through all the finite layers of belief in rationality at up to omega-fold belief in rationality, we see that player 3 must already believe with certainty that the other 2 players are going to choose the 1/3 quantities, and hence E is uniquely rational for him after up to k-fold belief in rationality for all finite k. So actually, we can't find any fixed belief for choice n that rationalizes n and that also survives those omega layers of belief in rationality, even though the choice itself survives omega steps of elimination of non-best replies. So the game actually only features the omega layers of strategic reasoning, as looking at the first order beliefs make clear. And it only features an additional step when we look at elimination of non-best replies. So that really strongly suggests that non-best replies, that specific procedure, is the culprit here and not the strategic reasoning in infinite games. And that's also borne out by my general results. Here's the result concerning the reasoning side. Really nothing interesting happens pretty much. Up to k-fold belief in rationality for all finite k is the same thing as common belief in rationality, and it is the maximal depth of belief in rationality in all games, finite or infinite. Now, if we look at non-best replies and whether that determines and when that determines behavior consistent with common belief in rationality, then it gets a little more complicated. In general, strategies are rational under common belief in rationality if and only if they survive alpha-fold elimination of non-best replies for arbitrary infinite ordinals alpha, and only under certain assumptions. Those here are the most permissive ones that I know: compact Hausdorff strategy sets and utilities that are continuous in first order beliefs. Only under such conditions do we get the one-to-one correspondence between non-best replies and CBR consistency. Strategy is rational under common belief in rationality if it survives omega-fold elimination of non-best replies. So here we see that the transfinite eliminations are really just related to the non-best reply elimination procedure. Let's zoom in a little bit on how the non-best reply elimination causes those transfinite steps. Now, the reason is really non-best replies selects only strategies consistent with belief in rationality. But the behavior that's consistent with up to k-fold belief in rationality for all k does not imply that this behavior is also consistent with common belief in rationality. And it's really this information loss going from up to k-fold belief in rationality proper, so something that talks about strategies and beliefs, to up to k-fold belief in rationality consistent behavior. That is what causes the transfinite eliminations. Here's a nice picture that illustrates this a little further. That's how belief in rationality goes through different levels. We start with a strategy belief hierarchy combination at the top here. Then we first ask, is the strategy rational for the belief? That's going to give us in the second step constraints on the strategy and the first order belief. Then we can go on, we can ask, is the strategy also rational for a belief that expresses belief in the opponent's rationality? And now we're going to get constraints on the strategy, the first order belief, and the second order belief. And all the while, what's going to be carried along and continues on and on like this, of course, going to common belief in rationality. All the while, what's encoded by elimination of non-best replies is going to be only those behaviors here marked in blue, the strategies that survive. But what is discarded by non-best replies is all those constraints we get on the beliefs, whether or not those beliefs are really consistent with the layer of reasoning that we're currently looking at. So I'm going to show you how this pans out in the second example. It's a little more complicated. The players 1 and 2 here, they choose strategies from 2 countable sets, A and D. payoffs follow from this matrix. I'm not going to delve into that. What's important is only this here. We have kind of a hierarchy of non-best reply elimination. If we look at the strategies D2, D3, and so on and so forth, D2 is irrational. D3 is only rational given D2 is possible. D4 is only rational given D3 is possible, and so on and so forth. So that means for every K at a K-fold elimination of non-best replies, strategy DK plus 1 drops out. It turns out strategy D1 is only ever rational if any of those other D strategies are available. So that means after omega steps of non-best reply elimination, strategy D1 is eliminated. And then it turns out we can go on with the A strategies because, well, the A2 strategy is only optimal given that D1 is available. The A3 strategy is only optimal given A2 is available. You see how this goes. So at every step after omega fold elimination of non-best replies, we step by step eliminate one of those strategies going from A2 all the way to infinity. Yeah, and in the end, that way we eliminate all the A strategies starting at A2. So everything except for A1, and that's going to be the single strategy that survives after 2 omega fold elimination of non-best replies in this game. Now, so if you go back to my results for this game, we have those steps omega to 2 omega of elimination of non-best replies, and somehow they must be jointly equivalent to that one step omega of belief in rationality. So how can this work? Now, to see how this works, we really got to look at what constraints belief in rationality at different levels puts on players' behavior and their beliefs. Now, if we do this, we see that at common belief in rationality, the following happens. If we look at all the strategy belief combinations that are consistent with common belief in rationality, what has to be true? Well, we already know none of those strategies can be any of the D strategies starting at D2. They have already been eliminated at the finite steps of non-best replies. So far, so clear. Well, but we can't stop there because also the beliefs are constrained, right? For example, the first order belief, my first order belief, I shouldn't deem possible any of those strategies in my first order belief either, the D2, D3, and so on and so forth. Well, but the D1 strategy can only be rationalized if I deem those guys possible. So if I eliminate all first order beliefs that deem possible D2, D3, and so on, and I eliminate all the strategy belief combinations involving those, then I also eliminate the strategy D1 entirely. Okay, but now let's look at second order beliefs. Well, the second order belief should also be such that I don't ascribe any first order belief to my opponent, such that this guy deems those strategies possible. Again, D2, D3, and so on and so forth. But then that includes all those second order beliefs include all beliefs that rationalize my strategy A2, because, okay, that only is rational if D1 is deemed possible. Well, and D1 is can only be in my first order belief under, can only be in my first order belief and be optimal for my opponent if I think my opponent deems those D2, D3, and so on and so forth strategies possible. So A2 has to drop out because of the constraints on second order beliefs. And we can go on and on in this way. If we go omega reasoning steps in this way down the belief hierarchy, well, we see that any strategy belief combination such that the belief deems possible those D2, D3, and so on strategies at some level has to be eliminated. But those strategies have to be deemed possible at some level in any strategy belief combination where I want to rationalize something different from A1. Hence, everything except for A1 drops out as a strategy that's available to me, and A1 is the only strategy that's consistent with common belief in rationality. And this way we see that really all those infinitely many steps of non-best reply elimination get crammed into just that one step of belief in rationality. As it were, the rationality constraints that come into the belief hierarchy at infinitely many levels here at common belief in rationality, they fold back and they trigger these infinitely many eliminations all at once. All right, let me conclude. So as we see, especially in this example, transfinite eliminations have very little to do with strategic reasoning. Rather, it's really an artifact of describing the behavior consistent with that reasoning with a specific method, elimination of non-best replies. We can take this a step further too, and we can find different methods of describing the behavior consistent with common belief in rationality. And what we're going to do there to get to shorter procedures is we're going to look at strategies and their supporting beliefs. In particular, as the example already suggests, here's something that always works if we want to get all the way back to omega steps. Just start at step 1 by eliminating strategy first order belief tuples. Then at step 2, eliminate strategy second order belief tuples, and so on and so forth. That's my theorem 3.3 in the paper. That concludes that concludes my discussion of the paper. One meta conclusion to end on. In a way, this whole problem that's been troubling us around transfinite eliminations, as we see here, you could say is really about the law of the hammer. If you only have strategy elimination, everything's gonna look like a reasoning depth. But once we bring in the epistemic tools, everything gets pretty clear and easy. Actually, the problems go away because we just explicitly model the strategic reasoning here, rationality and common belief in rationality. And we can now clearly distinguish that from a procedure that selects the common belief in rationality consistent behavior with strictly less information, but just under certain assumptions then, of course. Thank you very much.